Good afternoon, professors, guests, and students present. We're here today to present the second part of our engineering project, which we have called Part with Us. With you today, Darwin Gonzalez,
Pilar Rodriguez,
Jeffrey Liu, and your servant, Lux Gonzalez. Let's first understand the problem statement of this project. We wanted to help with the issue that our community faces, which is the lack of parking spaces. This can, of course, affect the time that people take to arrive at their destination, and this can also contribute to frustration in the different professors, staff, and guests on campus. The project itself is divided into two different parts, which is the central system, which is responsible for processing and storing the data for the functioning of the system, and then we have the subsystem, which is composed by sensors, the Wi-Fi board, the power supply, and management units. It mostly relies on concepts of wireless connectivity, sensor technology, and data processing.
So this is our first prototype, and we have different views of it, and this is how it looks in the outside and in the inside. And in the next slide, we actually built 5 more, so in total we have 6, like we can see over there, and they basically look the same. However, they look different in color, just because the 3D printers run out of the same color. And in the next slide, this is how it looks in front of the vehicle in the parking garage, and it is approximately half a meter away from the floor. And the next slide, we have the key components of our device. We start to the left with the ESP, which is our Wi-Fi microcontroller, and it connects our device with the main computer. It's sending the information gathered from the ultrasonic sensor that is water resistant and dust proof. We also have the ATtiny85, which is another of our microcontrollers, and it allows our device to go on sleep modes in different time cycles for energy efficiency. We are also using the MCP, which is a voltage regulator, and it regulates the voltage from 3.7 volts from the battery to 3.3 volts. It's the voltage that our device supports. In the next slide, we have also different other components like the battery. The battery is a 3.7 volts battery, and it has a circuit that prevents from overcharge, explosions, and discharge damage and other power failures. We are also using a PCB board and an ESP adapter. In the next slide, we are also using secondary components like capacitors, diodes, transistors, and a red LED that indicates when the battery needs to be recharged. In the next slide, we have this is how it used to look. This is a KiCad model simulation of how it was gonna be. However, in the next slide, you can see how we actually build it with all the components soldered, and we use a PCB board to optimize the size.
Now moving forward to the functionality of the circuit, we have first the ATtiny sending the trigger pulse to start the possibility readings. After that, the ATtiny gathers the information received from the sensor, and it will compare this to the previous status that we previously collected from the ultrasonic sensor. After comparing the two status, then the ATtiny will evaluate if it should send the high pulse or not to the large power circuit. This is in order to activate the ESP electricity circuit, which is the Wi-Fi microcontroller. And in order to save power, we only want to activate this microcontroller when we need to update information to the server or to the user. After the Wi-Fi microcontroller gathers the information for the ATtiny, it will send this information to the server, and after that, the ATtiny will go to sleep for 8 seconds, which is the amount of time that we have decided. It can be changed to 1 minute. It depends on how often a car parks in the parking garage. Moving to the next slide, explaining now the schematic. As previously mentioned, we have the battery source as the power input of the circuit is 3.7 volts, followed by the voltage regulator to reduce that to 3.3 volts. And we also have 2 capacitors for better stability for the voltage regulator. In addition, we have a connection between the ATtiny and the Wi-Fi microcontroller to the pin 2 and pin 21. This is to receive the message of the parking style will be empty or occupied. Also, we have a connection between the ATtiny and the sensor to set the trigger and also receive the information from the sensor. In addition, we have a connection to the large power circuit in order to send the high pulse that will activate the Wi-Fi microcontroller. monitor the battery level, and turn on an LED when battery charging is required. Moving to the next slide, an explanation of the programming of the ATtiny. First, we started by declaring two variables to store the previous and current status, because then we want to compare them and see if they are different or not. Then we start with the distance measurement. The distance measure that we show is 75 centimeters according to our testing. We also establish the voltage threshold of the battery in order to turn on the LED when needed. On the other image, we have the code in order to send high pulse, depending on how the variables are. And after sending that and the message to the ESP, the ATtiny will go to sleep mode for 8 seconds. Moving to the next slide, we are also using the MQTT communication protocol. This is a messaging network that allows clients and servers to connect without a direct connection. So in our system, the clients are each of the 6 sensing devices. They will be publishing the information to the server. And the server is the Eclipse Mosquito, which is an open source, and it was downloaded in a Windows computer, and it is gathering information. Another client that we have that is subscribing to information is in this case an MQTT Explorer, which is a software that we also have to see a better representation of the information. And also another client that can be either a web page or an application. Moving to the next slide. Now the explanation of the ESP. Since we are using internet, we have to specify the Wi-Fi credentials. We are using my personal cell phone as the hotspot because the Wi-Fi in some areas of the university, like the parking garage, is not good. So I have to specify my username and password. And also I have to add a specific topic to each of the sensors. So we have 6. So it would be from A to F, and they will be pushing the information to each specific topic. Also, the ESP will gather the information from the ATtiny of the message saying either it's empty or occupied, and it will publish it to the server. Moving forward to the next slide, we perform some testing in the lab. Moving forward, now we are blocking sensor B, so we should see the information being from empty to occupied in a couple of seconds. Remember that we have a sleep time of 8 seconds, so it's going to take some time, and we can see the updated information. Now we are moving to E and F, so we should see the updated information in a couple of seconds, as you can see over here. Then I remove the blockage from B, so B should go from occupied to empty, so we should see that as well, and we are keeping E and F as occupied. So B goes to empty, and now E and F should go to empty, but A should go to occupied. So we should wait for those 3 updates. F empty, E empty, and we are waiting for A to be occupied, as we can see over here. Moving to the next slide.
The mechanical side of this of our electrical device, it consists of 2 main components: ABS plastic for its high impact resistance, high malleability, and ability to absorb moisture for outdoor applications, and for the fasteners to ensure that most internal components inside doesn't get stolen. We're using stainless steel hex head stainless steel fasteners for its ability for corrosion, high resistance to temperature tolerance, and stress. Next slide, please. Here's an overview of the case. As you can see, in the middle is the ultrasonic sensor. Top of that is the battery holding case with a snap hook lid for keeping the battery enclosed inside of the case, as well as a front lid. Sorry for the lack of being able to see it properly. Please, next slide. For the drop test, it was performed in 2 different scenarios. The first scenario was an ideal case of SolidWorks in an ideal environment where there is no drag force or dynamic rotation for the device, and the second is a physical drop test of these devices that you see in front of you. Please. Here, the ideal case, the processing for SolidWorks took about 40 microseconds for it to impact the floor post-impact, and the time-dependent von Mises stress. The maximum stress that the device experienced when it hit the ground was 40 kilopascals, definitely within the limit of the elastic modulus as well as the Poisson's ratio, and it shows that that it will begin permanent deformation or fracture through the material. Please.
Here is another time-dependent displacement analysis as well as the post-impact impact of the same time frame of 40 microseconds. The deformation of plastic deformation that the plastic case will experience was 0.25. It says that it's elastic, but in the ideal world, it is elastic, as you will see in the next slide. But in physical, you will see that it predicts something quite different. Please. Here on the left-hand side is the von Mises stress. As you can see, the color deformation changed throughout the distribution of stress throughout the plastic case in an empty environment. Wasn't able to add the electrical components into it, but that's how the stress distribution will distribute through the case, as well as the displacement on the bottom. In the ideal case, it lands flat on his face. Next slide, please. Here is I performed the physical test here in this building on the second floor, from the ceiling tile to the floor, which is approximately 2 meters or 6.5 feet. The test proved that it does show potential weakness in the corners as predicted when hitting the ground, but this is also due to dynamic performance of force drag as well as dynamic rotation as it hits the ground in that short amount of time. Please.
Passing to the user interface, once we have gathered all this data, we inform to let the user know exactly which units are available. So we decided to create an HTML file, which first checks if the system is operative, if the server is transmitting, and then it changes the color of the different squares. Every square be representing one of the different units. We, as event handlers, we have 3 different connections. We have the on-connect, which is the one that subscribes to every individual topic within the MQTT server, and failure will be the message displayed after we ensure that we are not receiving the data that we're supposed to show, and on message arrive is the one that changes the color of every individual square. One of the main benefits of the web sockets over the HTTP protocol is as we increase the number of users trying to use our platform, it is better because it has a one-way connection which allows every user to connect individually to the server without any delays. This is also very useful for our application because the communication is live. It also makes it very easy in the future to make a type of subscription that could offset the cost of the project. As for the budget, we spent $382.82 for 6 units. Our unitary cost is $58.64, and we spent having all the cases printed and all the pieces together around 1 hour to build and program every individual byte. 400 units with these unitary costs, we are at $5,864. But if we wanted to pass into a large-scale production, we would need to change some things which would later affect the unitary cost. These are scheduled for spring. This is the flow we followed. We wanted to create the reports, get the material selection, and a prototype done before the end of the semester. And then this semester, we're focused on pulling that one prototype, making the production, testing every individual unit and all of them together, and then today our final presentation.
Then moving to the ethical part, although our design, our device don't present a significant hazard for the community or for the environment, we still review different code of ethics of different institutes. That's why we consider the use of rechargeable batteries, so we can, for the proof of concept, so we can reduce the waste. However, if we plan to make it in a mass production, we will require hardware.
Now moving to the most important test, we have here B, E, D, and F. Right now, sensor E is pulling out, so we were occupied and now we received the data information to be empty. Next, we are going to test sensor with letter D. Is currently occupied, so it should go to empty in a couple of seconds, as we can see over here. After this one, we are going to test sensor B. Is currently occupied, and we are moving forward, so we are going to keep it as occupied and receive that information in a couple of seconds as well. As we can see over here, it didn't go updated, it kept us occupied. Lastly, we tested sensor F. It's currently occupied, as you can see the blue card, and is pulling
the public in general. We would like to take a second to acknowledge our professors, our advisors for the first and second part of this course, our peers, and the drivers that help us through the testing phase. And that was Arvidas.
Thank you.
Could you go to the slide that shows the electrical system?
Yes, sir.
There you go, yeah. You've got two different microcontrollers there, and it looks like one controls whether the other one is operating or not. Is that
Yes,
the idea?
yes,
Okay, I guess the idea is you save power by only operating the one routinely. I'm not familiar with these particular microcontrollers, but most modern microcontrollers have sleep modes and power saving modes that you can go into. And it just seems like to me you're making things overly complicated. But I'll tell you this, from what you were showing, it looks like you've got a system that's working, and working beats not working any day of the week.
Sir.
And I'm impressed that you have something that seems to be at that stage of development this early in your senior project. So I'm not suggesting, that you've done anything wrong. I just wondered if there might be some power-saving modes that could accomplish the same thing with a simpler design with only needing one microcontroller instead of
but
two.
yeah, last semester we performed,
You've looked at this, I assume, and if you've got a system as complicated as what you presented here working, and it looks like you do, I'm not going to argue.
no, I wasn't going to explain, so last semester.
I'm impressed.
Thank
So, good job. Thank you.
Appreciate that. Thank
This
you.
is their second semester. This is their second semester. They're done.
Yeah. Oh, this is the final.
Yeah, we're seeing project.
It shows it.
So Jeffrey, you know it's going to be a point contact when you drop that.
Correct.
Why didn't you simulate the point
If,
contact?
can we go to,
Because when you drop it, it's very possible you stop a plane contact. It's most probably it's a plane contact.
it is, to model an angle, I use different software programs. The first dynamic program that tested the displacement and von Mises stress, Professor, is that I used Abacus simulation. However, there was some discrepancies as the plane that I chose as the ground, the material would phase through. It would not hit the object as if it was a rigid object for some reason. So I had to work with what I got within the time frame that I was given to simulate something that would give an ideal situation as not necessarily the most worthy case. It's kind of simulating what Darwin mentioned, or the 1.5 feet drop from where it would be posted, and as it hit the ground, that's something similar. The worst case scenario in the physical drop would be the worst case scenario is if we mounted the system above the vehicle out of eye shot, so if not an eyesore inside of if we're trying to keep things pristine, that's the reason why. However, I could have adjusted the plane so that it could contact on a general corner section. Maybe for further analysis, if I had more time, most definitely I would have definitely put those type of video slides in there to test that type of environment for it impacting in a corner.
So this is in Abacus?
No, this is SolidWorks, Professor.
Oh, this, okay. So is it pretty hard to change the orientation?
No, sir, it is not. It's just basically changing, determining your reference plane, and then from that reference plane, deciding which angle to manipulate. And You can control the direction of travel by selecting a specific face or a specific corner that orients the direction of fall during this dynamic test.
So, we have our second. Here, you try really hard to save energy, right? That's a whole your design. So do you have a general ballpark number of how much energy, like if the system is fully on, how much energy you're saving? Like is it 30% or 70% or 90% of like?
I don't have a percentage because it will depend on what components we have on. I have a rough calculation when all devices, when all components, the baking dining, the ESP, and the sensor are on, the power will be around 270 watts, 75 milliwatts. If they are in idle state, it would be 0.168 milliwatts. But it can also vary because depending on if the sensor is reading or no, or if the ESP is on or no, so we would have a constant power.
So based on your general feeling, like are you able to extend the battery by 5 times, 10 times,
Yes.
or like what's the general thing?
Yes, so if we go to one of the final slides, I have some improvement that we can move up this schematic. That one. So some improvement that future students can add to the system is adding that diode and the resistor so that when the 8090 sends the high pulse to the large power circuit, it can get the ESP to turn on by itself. So we wouldn't need the 8090 to be constantly sending the high pulse. So at that time, we can only have one microcontroller on at the same time. So the ESP could be on, receiving information and sending it to the server while the 8090 is sleep mode. So in that way, we can save some power.
So long term, if this were a commercial product, how would you address the like issue? You understand what I'm saying? Like if this is like it's gonna be like you must install like a very powerful through the wall and just try to like amplify or whatever to amplify the signal to make sure that region has good Wi-Fi. That's essentially necessary. Right?
So the ESP has an onboard antenna that has a range of around 150 meters to 200. So yes, it would depend. If you have a router close to that area, then it
But
would be
based on your design, it sounds like you must have very good Wi-Fi to make the system
Yes.
work, right?
Yes.
So that's something user must address first before they install the system. Right?
So the last test on the market, so it seems like in the car is in the from the sensor and shows that the actually.
Can you go to the video?
So the last one, so the
We show the cars.
so how far from the sensor?
75 centimeters.
75, which is about this 1.5 feet. Which is normal place for a lot of people to park. People who park all the way close to the wall. A lot of times, is it something that you can define for the sensor? You kind of, can set, so 75, like a meter or something, or that's something you really need to do with the sensor? How's that?
It can be changed. But since we solder them, then we will have to remove them and program them again. But yes, that can be changed.
So you can basically define the entire length of